Alright, let's go a little deeper into binary trees. So I want to talk about two properties of binary trees, um, which are called height and balance, and they're closely related to each other. And to talk about height, we need to talk about a property of nodes of a tree, which is called depth. And depth is a pretty simple concept to define, but it can be confusing to actually work with. So here's a binary search tree. Depth of a node, so this is a property of an individual node, equals number of steps from the root to the node. So for example, this node right here, how many steps are there from the root to this node? Well, if I start at the root, I have to travel 1, 2, 3, 4 steps. So the depth of this node is 4. And similarly, the depth of this node is also 4, because from the root I travel 1, 2, 3, 4 steps. And if I've drawn my tree in a nice even way, what I will find is that, all the nodes down at this level will have the same depth. In other words, this node right here, from the root I travel 1, 2, 3. This node has a depth of 3. This node, from the root I travel 1, 2. Depth is 2. Well, this node, same thing, 1, 2. Depth is 2. This node I travel 1, 2. The depth is 2. This node over here, we noted it had a depth of 4. And from the root to get to this node is a single step. This is a depth of 1. And a single step gets you here. This is a depth of 1. The root is a special case. How many steps do I need to take to get from the root to the root? I don't have to take any steps. So the root is at depth of 0. And so depth is basically how far down you move vertically from the root of the tree to get to a given node. And these are just pointers in memory, but if we draw a picture of our tree like this, where we move down the same amount each time we go from parent to child, we'll find that everything sitting at this level has the same depth, everything at this level has the same depth, everything at this level, and so on. So depth is a notion that makes some intuitive sense, right? It's how deep we are traveling from the root to get to a node. Alright, so that's the depth of a node. And related to that, oh, and by the way, this is well defined, right? We're saying start at the root and see how many steps it takes to get you to a node. That is a well-defined number, right? And it's well defined because there is only one path that will get you from the root to a node. And that's a consequence of a fact that there are no cycles in our tree, right? There's no way to start at the root and follow one path to get to a node and then follow a different path that will also get you to the node. If that happened, then somewhere in that chain, a node would have more than one parent. And in a binary tree, every node has exactly one parent except for the root, who has no parents. Alright, so depth is a well-defined quantity. So we can define the height of a tree, and that's the depth of the deepest node, or nodes. So this tree, we find two nodes with a depth of 4, a node with a depth of 3, 3 with a 2, 2 with a 1, and one root with a depth of 0. The deepest nodes have a depth of 4, and so for this whole tree, the height equals 4. So the height of the tree is, just like in the case of a real tree, it's the distance to the tallest part of the tree. Well, the height of a binary search tree is the depth of the deepest node. And if we have a tree containing just a root, the height of that tree would be 0. It still has a node, but it's considered to be at a depth of 0. But there is an edge case. If we have a tree containing no nodes at all, so a tree whose root is null, we define the height of that tree to be -1. And this is like the same way we define 0 factorial to be 1, or a number raised to the 0 power to be 1. This makes a lot of things work. And there's other ways of looking at height that will make this meaningful, but we'll just take it as a definition that if we have an empty tree, the height of that tree is going to be -1. That's just the definition. Alright, well, why is height important to us? Remember, when we have a binary search tree like this, and we want to look for a number, we move down the tree at each operation. So we start at the root. Let's say we're looking for a number, and it's bigger than the root. We're going to move down one level. If we find the number's bigger than that, we'll move down another level. If it's smaller than this node, we'll move to the left, down another level. If it's bigger than this, we'll move to the right, down another level. So whatever the height of the tree is, that's the depth of the deepest node. That's the number of steps that you might have to take from the root to get to that node. That might be on par with the number of operations you have to do to either find that node or reach that node, see that it has no children, and decide your number is not in the tree at all. So the number of operations is on par. So the number of ops is close to the height of the tree. Right? Now, I mean, if we're looking for, this number right here, we'd only have to do 2 comparisons to find our data there. But worst case behavior, you might have to start at the root and travel all the way down to a leaf node, and the deepest leaf is the height of the tree. So worst case, we might have to go down that far. So the height tells us, something about our order of complexity, about how much work we may have to do. All right, so height ties into the notion of balance. And so let me give you an example of a binary search tree. Right, there's 7 pieces of data stored in a tree. The height is equal to 2, right? 1, 2 gets us down there. Which means worst case we have to do 3 operations to search for a number. If we want to find a 30, not there, not there, there it is. If we want to find a 35, not there, not there, not there, it's not in the tree. So this is a nice log n, where n is the number of nodes in this tree. Well, let me show you another binary search tree that has the same information in it, but stored differently. Right? So this is a binary search tree. Each node has 0, 1, or 2 children. Every node has a parent except the root. Everything to the left of a node is smaller, and anything to the right of a node is larger. This is a binary search tree. But it is not a very good binary search tree for searching, right? If I want to search for the number 3, I'm going to compare it to this, and this, and this, and this, this. It's less than 5. I'll look to the left. There's nothing to the left. 3's not in there. Well, I have 7 pieces of data, and it took me 7 operations, right? So our operations on this particular binary search tree are going to be closer to order n. This is nothing more than a linked list, which, for searching is no better than an unordered array. It's order n. So the same set of data, the same collection of numbers, stored in 2 different binary search trees. This one gives us really nice behavior. This one gives us really slow behavior. So we would like a way to look at a tree and say, hey, is this a nice behaving tree, or is this a kind of pathological tree that's going to give us really bad orders of complexity? And so there's a notion of balance. And intuitively, right, the reason that this is not giving us this nice log n behavior is because when we eliminate the root, we're not cutting the data in half. We're eliminating one piece of data, but we still have these 6 numbers to search for. And if we're looking for a number smaller than 40, we get rid of the 40, but we still have 5 numbers we need to search in. Whereas this tree up here, which is balanced, if we decide that our number is bigger than the root, we get rid of half our data. And if we decide our number is smaller than the root of this subtree, we get rid of another quarter of our data. And now we're down to 1/4 of the original problem size. So a balanced tree is one that preserves this property of cutting things in half when we move left or right, which means we should always have kind of the same amount of stuff on the left and the right. That's the balance, right? This tree is very lopsided on the left. There's nothing on the right, a lot of stuff on the left. This tree is very evenly balanced. If we look at the root, hey, there's 3 things to the left, 3 things to the right. In fact, this is perfectly balanced. Because at any node, if we look at the left and right subtrees, there's the same amount of stuff in each of those trees. Alright, so let's dig into this notion of balance. And balance we're going to define recursively. And so here's the definition. So a binary search tree, T, is balanced if T left is balanced and T right is balanced and the height of T left minus the height of T right if those are within one of each other. So the absolute value of the difference in height should be less than or equal to 1. Or there's an edge case, T is null. Otherwise, T is unbalanced. So that's our definition. That's what we're going to use when we ask the question, is a tree balanced or not? So for this tree to be balanced, we need to know that the left and right subtrees have a height close to each other. While the height of this left subtree is just the depth of the deepest node, this node has a depth of 1, 1. So the height of this tree is 1. The height of this tree is 1. So the left and right subtrees have similar heights. So this whole tree is balanced if that's balanced and that's balanced. It's recursive. So how do we know if this is balanced? Well, the left and right subtrees need to have heights within one of each other. While the left subtree is just a root, that's a height of 0, so that's fine. But we also need this tree to be balanced and that tree to be balanced. So let's look at some trees and see whether or not they're balanced. Let's look at a tree containing a single node. So is this tree containing a single node balanced? Well, the left child is null. And we've said a binary search tree T is balanced if T is null. So the left tree is balanced. And the right tree is balanced because the right tree is null. And the height of the left subtree, well, remember the height of a null tree is -1. And the height of the right subtree, which is null, is also -1. -1 minus -1, that's 0. That's less than or equal to 1. So yes, a tree containing a single node is balanced. And a null tree is also balanced. Well, since a tree containing a single node is balanced, both of these trees are balanced. and they both have a height of 0, and so this tree is also balanced. So that's a balanced tree. But it turns out this tree will also be balanced. And why is that? Well, the left subtree is just a tree with a single node, which we already said was balanced. The right subtree is null, and we know a null tree is balanced. So that's satisfied, that's satisfied. Let's look at the heights. The height of the left subtree is 0. The height of the right subtree is -1. And 0 and -1 are within 1 of each other. So this is balanced. This tree, on the other hand, is not going to be balanced. So the left subtree looks like this, and we just saw that's balanced. The right subtree is null, and we know a null tree is balanced. But the height of the left subtree, well, this tree has a height of 1. The right subtree is null, that has a height of -1. And 1 minus -1, that difference is 2, which is bigger than 1. So this is not balanced. So we can start to develop an intuitive notion of what it means for a tree to be balanced, but this is the definition. And we always want to come back to the definition and make sure that that's what we're using to decide whether or not a tree is balanced. And so we can code this. We could write a balance function that takes in the root of a tree, t, and just does these things, right? Now the first thing we would want to do is see if t is null. So let's put a comment here and say check this first. Right, because if t is null and we try to look at t arrow left, we're going to segfault. So our balanced function could first say if t is null, return 1. It's balanced. Otherwise, see if t left is balanced, and then see if t right is balanced, and then see if the height of t left and t right differ by no more than 1. And if all of those things are true, the tree is balanced. Otherwise, return a 0. It's not balanced. And so our balance function is nothing but a bunch of function calls. One subtraction with an absolute value statement, right, which we can do with an abs function or with 2 ifs, and a check to see if our tree is null. So again, a really, really easy function to write. The computer has to do a lot of work to run this function. It's going to take our tree and it's going to recursively check to see if it's balanced at each point in the tree, right? But we could have a tree with 1,000 nodes, and this simple function will go down and explore all the nooks and crannies of that tree and come back with a final answer saying, hey, the tree's balanced or it's not. And our intuition for what is a balanced tree may fail us. Right? Is this a balanced tree? Well, you might think it is, you might think it's not sure. But we apply the definition, right? So the left subtree, well, that's balanced. The right subtree, well, it's going to look like that, but it's a mirror image. That's going to be balanced. And the height of this left subtree is going to be 1. The height of this right subtree is going to be 1. Those are within 1 of each other. So this is balanced. But this is not going to be balanced. And we know it immediately because the first check is the left subtree balanced? Well, the left subtree is this thing, which is not balanced. Since the left subtree is unbalanced, the whole tree is unbalanced. So this is not balanced. All right. So we can use that definition to write a function to check balance. And let's look at how we calculate height. We talked about height of a tree a few minutes ago. And we said we basically want to find the number of hops from the root node to the deepest node. And so we could, traverse the tree and record the depth of each node as we go. But there's a recursive way we can define the height of a tree. So imagine we have a root node, and then we have some subtree on the left and some subtree on the right. Alright, the height of this tree is the number of steps from the root of this tree to the deepest node. The height of this tree is the number of steps from the root of this right subtree to the deepest node. Whichever one of those is largest, the number of steps from root to the deepest node of the tree will be one step to get to this node, plus the number of steps from this node to the deepest leaf node. And so if you think about this, the height of the tree equals 1 plus the maximum of the height of the left subtree and the height of the right subtree. And the intuition here is that if we want to find the maximum number of steps from the root to the deepest node in this left subtree, it's just one more than the maximum number of steps from this root to any node in that tree. So whatever the height of this is, if we add 1, we'll find the height of this, assuming that there's not a deeper node on the right side. But if there's a deeper node on the right side, then the height of the whole tree will just be the height of this subtree plus 1 more. Well, we don't know which side has the deepest subtree, so we calculate the height of the left and right subtrees, find the largest value, add 1. And of course we need an edge case, height equals -1 if t is null. Otherwise the height is 1 plus the height of the largest subtree. So that's recursion coming in again to save us from actually moving through to each node and calculating the depth. We have a recursive definition. And this is, 2 lines of code, maybe 3 lines, if you don't have a max function. And it perfectly matches the intuitive notion of finding the height of a tree. Right? Find the height almost to the top, and then just add 1 more. Alright, so we'll talk more about balance when we talk about AVL trees. AVL trees are a way to store data in a tree and keep our tree balanced, so that if our tree starts to look like this, where it's not nice and full and fluffy, we can rearrange the nodes. Because intuitively, the idea of a balanced tree is we want to keep as much stuff stored near the root before we start going too deep. So we'll talk in a future lecture about how we can make that happen. And the algorithm we'll talk about is something called an AVL tree. But what I want to wrap up this lecture with is the subject of deletion from a binary search tree. How do we delete a node in a tree? And that's a little trickier, so we're going to talk about an algorithm for doing that next. Alright, so deleting from a binary tree. There's an easy part and there's a complex part. In this case, the easy part is actually the recursive aspect of deletion, and the non-recursive base case is the one that gets really complex quickly, but we'll take it apart in pieces and get through it. But let me talk about the recursive part first. So suppose we have a tree, let's just say, 40, 20, 10, 30, 60, 50, 70, and there could be more stuff hanging off of here, and so on. So a tree with a bunch of stuff, and suppose we want to delete the 20. Alright. All we have to do is say, hey, 20 is smaller than the root, so 20 is somewhere in this tree. Delete 20 from this tree, and replace this tree with what you get when you delete 20 from this tree. right? It's a passing the buck. It's a recursive notion. If I want to delete 20 from my original tree, just delete it from this subtree and replace this subtree with your new, version of this with 20 deleted. And as long as you know how to correctly delete 20 from this tree, we can replace this with that new tree, and our original tree will still be a binary search tree. Because originally everything smaller than 40 is over here, and if we just delete 20 from this tree, everything over here will still be smaller than the root 40, and so this will still be a BST. And if I want to delete 10 from this original tree, just look at the left subtree and say, hey, delete 10 from this tree, and replace this tree with what you get when you delete 10 from it. So just take this out, replace it with a tree that's missing 10, and leave that as the left subroot of the root, and you're good to go. And similarly, if we want to delete something that's bigger than 40, like say we want to delete the 70, well, we'll just say delete 70 from this tree, and there could be more stuff coming off of here. But we'll say, okay, just delete 70 from this tree and take that new tree, plunk it in right here, and we've got our original tree with 70 removed. So the recursive part is pretty easy. So let's just say delete root, comma, data. If data is less than the root data, let's call delete on the left subtree. Delete data from that. And then whatever we get back, let's make the left subtree that modified left subtree. Else, if data is bigger than the root, then let's set the right subtree equal to what we get when we delete our data from the right subtree. So delete from the right subtree and replace the right subtree with that. So this delete function, just like our insert function, needs to return possibly a new root. So a struct node star. So that's the recursive part, but that's the easier part to understand, right? We're just passing on down the line. Hey, I want to delete a 30 from this tree. Okay, do whatever you have to do to delete it from this, and then make that the left subtree of 40. And we're done. We've removed the 30. So the trickiest part is when we need to delete the root. Because if the data is not less than the root and it's not bigger than the root, it's equal to the root. So all of our subsequent discussion on deleting from a binary search tree is going to focus on how do we delete the root of a BST. And the trick, of course, is that, if we just throw this thing away, we don't have a tree anymore. Number one, our root is pointing to something that's not part of our tree. And number two, we've got two subtrees where the roots of those subtrees have no parent, right? They're orphaned trees, and we have no access to any of the data in our tree. So the root is sort of the most critical piece of the tree, and deleting the root is the trickiest thing to do. But there's a fairly straightforward trick we can use to successfully delete the root of a tree. So let me show you a tree with some actual numbers. So let's say we want to delete the root, and that's all we're going to talk about the rest of this lecture, deleting the root of the tree. So we want to delete the 40. Well, obviously we're going to take this out of the tree, but we've got to put something else in its place. And of all the nodes that we could move in place of the root, there's only really one that will make the most sense. For example, if I move the 90 up here, this would no longer be a BST, because if this is a 90, this should be bigger than 90, and it's not. If I were to move the 20 up here to be the root, well, everything to the left of that root would have to be smaller than 20, and there'd be no place to put our 30 and our 35 and our 37. So what's the most logical node to put in place of the root? It turns out if we pick the largest node in this left subtree, we can safely move that up to the root. Because the largest node in this tree, everything else in this tree is smaller than that largest node. So the largest node is 37. If I made 37 the new root, everything over here would still be less than 37. And so this would still have the BST property, and BST is less than 40, so everything over here will be bigger than 37. So to delete the root of a BSTT, replace the root with the largest node in the left subtree. So we're going to take this 37, we're going to move that to the root. But we've created a problem. 37 had a child to the left. So we need to have somebody adopt this child. Well, we can have 37's parent adopt 37's child on the right. So step 2, if that node had a left child, let that node's parent adopt it on the right. So this 36 is going to come up and be the right child of 35. And we're done. We deleted the 40. The new root of the tree is 37. Everything over here is guaranteed to be less than 37. And the only thing we've changed was this 36. While it used to be to the right of 35, it's still to the right of 35. Alright, and this is always going to work. And it's going to work because since 37 was the largest node in this left subtree, 37 had nothing to the right. It could have things to the left. In fact, it could have a whole tree over here to the left. But it has nothing to the right, so it's only got one subtree that needs to be adopted. And since we're removing 35's right child, 35 can adopt this orphaned subtree. So let's just do a few examples of that. So here's 40, 20, 10. And there's some stuff over here on the right. The right subtree is not really going to come into it. So in this case, I would replace the 40 with a 36. Now, it's possible that the 36 could also have some other things on the left. So if I move the 36 up to the root, all of this is going to be orphaned, but I'm just going to take that and move it up here. So I'm going to take the 36, make that the new root, and then let 32 adopt on its right all the stuff that 36 used to have on its left. Alright, and this is not too bad to code. So let's imagine here's the root. And there's some stuff over here, and there might be some stuff over here. So let me call this largest node in the left subtree. Let me call this largest. And let me call the node right before it parent of largest. And we'll call the root root. So here in this particular case are the steps that we would take to delete the root. So we could do something like this. Parent of largest on the right should equal whatever is on the left of the largest. So that one line of code, parent of largest right equals largest left, will take all this stuff hanging off the left. Could be one node, could be null, could be an entire tree containing 1,000,000 nodes. It will take all of that and situate that subtree's root to be right here on the right of parent of largest. So that's where we adopt this subtree, which I'll just draw as a triangle. That's where we adopt it on the right of the parent so that it's not orphaned. And then we could say largest left equals, and we want it to be the root, so we can just set it equal to root left. And that's where this new root adopts the left subtree on its left. And then largest right is just equal to root right. So now it adopts the right subtree of the root on its right, and then we could free the root. So once we've identified the largest node and its parent, it's 4 instructions to actually perform the deletion, which is the replacement of the root of the original tree with that largest node and the adoption of that largest node's left subtree by its parent. So that's not bad, right? 4 lines of code. So why is deletion so tricky? Well, we got to do a bit of work to find this largest node and its parent. And it's just, another algorithm. If we're looking for the largest node in the left subtree, how do we find that? Well, start at the root of the left subtree and just keep moving to the right. And when you can't move any further to the right, that's the largest node. So if we're trying to delete the root of a tree, go down to its left subtree, right, and remember that node and just start a loop where you keep moving to the right. And when you can't move any further, the last node that you were at, that's the largest node, and the previous node, that's its parent. And if there's another node to the right, well, this is not the largest, right? Because anything to the right is bigger than that node. So by moving as far to the right as possible in this left subtree, we can find the largest node in this left subtree. It's the rightmost node. But there's a few edge cases that we need to think about when we're doing this. So let me show you a few possible complications. So there's a general tree. So we could say something like, temp equals root left. So temp is sitting right here. And then we could say next equals temp right. So this is next. And then we could say while next right is not equal to null. So if there's something to the right of this, we can simply move down. Next equals next right. And temp equals temp right. So next will be here, and temp will be here. Top of the loop, is next right equal to null? No, it's not. So we're going to move down again. We're going to set next equal to next right, and temp equal to temp right. Top of the loop, is next right equal to null? Yes, it is. There's nothing to the right of next. We exit our loop, and now next is our largest node, and temp is parent of the largest node. So in the general case, it's not a bad loop, right? You have to start at the root of the left subtree, find its right child, and then just start moving down and keep a pair of pointers, temp and next. Next is the node we're looking at, temp is its parent. When we can't move any further to the right, the node we're looking at is the largest, and the previous one was the parent. But the edge cases we need to worry about are the following. One is where we have a case like this, where the root of the left subtree has no right child. Because if this node to the right of the left subtree's root, if this 15 was null, right, our code would say, okay, set temp equal to root left, so this would be temp. Set next equal to temp right, well, next would be null. And this while loop is going to segfault. Right? In other words, our general prescription is let's move through this left subtree and get as far to the right as possible, remembering who our parent is. But if it's not possible to move to the right at all, if this is our subtree and this is the root and there's nothing to the right, our general algorithm is going to segfault. It's an edge case. So we need to identify this situation. And in that case, this is the largest node in the tree, in the left subtree. And our algorithm is simply, well, let's just adopt the original right subtree on this node's right side. So there's one edge case, moving to the left subtree. If there's nothing to the right of that subtree's root, then just have the right child be the right child of the original root. So we would go from something like, 20, and here's a subtree A, and here's a 10, and here's a subtree B. And in that case, we would make 10 the root, we'd leave B on the left, and we would just adopt A on the right, whatever this tree looks like. And that's an edge case because we can't do the usual business of looking down at children to the right of that 10. The other edge case is even easier to deal with, which is where we have a tree, but there is nothing to the left of the root that we're deleting. In other words, this is null. So we can't even come down and find the root of the left subtree because the left subtree is null. But if that's the case, we just have this tree with a root and then a subtree to the right, and we want to delete the root. Well, that's easy. Just change the root of A to be the root of the entire tree. So that's how we're going to delete from a binary search tree. So again, there's a recursive step to decide should we actually delete the root or should we just delete from a subtree and then, take that as our new subtree. When we get to the point where we're deleting a root, there's the general case, which is move to the left subtree, find the largest node, find its parent, and do these steps. There's a special case where we're in the left subtree and there's the root, and that is the largest node because there's nothing to its right. And in that case, we just move that largest node to be the new root and adopt the original root's right subtree on our right. And then the extra funny case where there's no subtree to the left at all, we're deleting the root, but there's nothing to the left, and in that case the new tree is just whatever the right subtree was. So we have to keep all those cases straight and check for those exceptions before we do the general case like this. But as long as there's a root of the left subtree and at least one child to the right of that, our general algorithm is going to work. So if our tree looked like this, we would start off with temp being the root's left and next being that node's parent. And then we'd say, well, next right is not null. Well, if this is the largest node with nothing to the right, we never do this loop. And so next is the largest node and temp is its parent. So next becomes the root, and anything to the left of next gets adopted by its parent on the right. All right, so the practice problems will take you through those different situations you want to try to get that code working. This stuff is really easy to make a small mistake and have things get totally crazy. Things that can go wrong, you can end up abandoning nodes, so you lose data. You can end up inadvertently creating loops so that when you try to traverse your tree, you just keep printing out forever and ever and ever because you're coming down but jumping back up to the top at some point, or somewhere you've already been, so you can see, infinite traversal behavior. So that's another problem. Or it could be that you end up deleting the wrong thing, or that you end up with, something that's pointing somewhere it shouldn't. Seg faults are very common in this code. General corruption. So lots of ways this can go wrong. This is where being able to go into the debugger and start from your root and, print star root, print star root left, print star root right, and make a picture of what your memory looks like, and then compare it to what you want your picture to be. That's going to be a really useful skill set. So the work we've done previously with using GDB to examine memory directly, that's all going to be really useful in getting these algorithms to work. All right, that's tree deletion.